Hi, I am Ruiyuan from the Chinese University of Hong Kong. This is a presentation of our paper titled PriPro Towards Effective Privacy Protection on Edge Cloud System Running DNA Inference. This work was done when I was an undergraduate student at Beihang University, and it is a joint work with MSRA and BJTU. Many thanks to my co-authors. There are 4 parts in the presentation. First, I will go through the background and motivation of our paper. Then I will present our methods. After that, I will show the evaluation of our methods. Finally, I will make the conclusion and talk about the future of our work. Let's get started from the first part. Despite the powerful generalization capability of deep neural networks or DNN, their computation demands are tremendous. Therefore, edge devices commonly collaborate with cloud services to boost the development of deep learning applications. In practice, to protect privacy while decrease the computing cost, a compromise is reached. The commonly adopted approach is to cut a deep model into 2 parts and run each part on edge device and cloud services respectively. As shown here, edge model takes the photo as input and output intermediate results. Cloud model takes the intermediate results and outputs a predict label. However, the photo accidentally contains a person and a car, while it is irrelevant to the information needed to identify the call. Therefore, malicious cloud service provider or network attacker may take the intermediate results and analyze the gender, age, and other private information in the image. For easier demonstration, we use user model to indicate the original DNA model, and user task for the task the user model is designed to complete. We use attacker task to indicate the target of the attacker, and attacker model is a method that attacker may use. In this scenario, we need to protect the privacy from the scope of single user input. The attacker we need to handle is anyone who can get the intermediate results. The intermediate results should only contain information about user task. Therefore, to protect privacy, we need to limit the information within intermediate results. Before we start to analyze methods, I'd like to talk about the metric in the literature. Mutual information metric is a common metric for privacy protection. It is also used in the paper by Marcella et al. And the paper by Orsia et al. However, the first problem about this metric for edge cloud system is that it only considers group privacy rather than parent privacy. This is also indicated by Wang et al. Also, we conduct some experiments showing that although MI is expected to decrease as the layer goes deeper, the results are not. This indicates that MI cannot measure the information loss accurately. Third, we perform a attack on several models that are evaluated as effective in privacy protection with MI. However, the accuracy of attacker task is still high. Therefore, MI is not sufficient as a metric. In the paper, Orsia et al. Proposed to use 2 metrics called privacy measure and transfer learning. We found that privacy measure requires the user model to extract features that has 100% accuracy, and transfer learning, like normalization, makes it hard for comparison. For more analytical comparison, please refer to our paper. Then, I will talk about privacy protection methods in the literature. First, differential privacy or federated learning focuses on training data rather than single user input for inference stage. Therefore, they cannot be applied in our scenario. Second, although cryptography methods can provide good protection of privacy, the computation cost by large amount of data for encryption is prohibitive for edge devices. Third, noise injection used by Shredder and DPFE is promising. However, Shredder uses a static noise parameter for noise injection. While it is easy to break, a DPFE is hard to apply because they design a new architecture rather than a pliable module. In summary, the drawback exists in both metric and protection methods. We propose a design criteria that privacy metrics need to be enforced to single user scale and consistent to real-world scenario in edge cloud system. as privacy protection methods need to protect individual input. The protection needs to be easy to apply and cost low computation overhead. This is also the motivation of our methods. Then, in the second part, I will introduce the new privacy metric called PA and PI metric, and then privacy protection method called PriPro. First, I will introduce our privacy metric called PA and PI metric. As indicated by the design criteria, we need to first revisit the real scenario of edge cloud synergy. Here, we formulate the behavior of user model and attacker. Then we can formulate the protection as an optimization problem defined as this. The objective is to optimize tool accuracy to opposite direction for each task. Therefore, we propose two metrics from the protection objective. To perform evaluation, the first step is to define the user task and the attacker task. Here I need to emphasize that attacker task here is only for evaluation. The protection method is not expected to know this. Then we train both attacker model and the user model normally to get the first pair of accuracy. After perform protection, we fix the model for edge and simulate the acquiring of intermediate results and train the parameter for two models on the cloud separately. Then we calculate PA and PI from this formula. The advantage of PA and PI method is that this metric evaluation privacy is from pairwise level and they are consistent to real-world scenario. Also, this metric is also flexible to change the task and model for attacker to suit for any application scenario. Now, I will show our method for privacy protection called PriPro. Notice that this method does not make assumption about attacker task or attacker model to make the whole method work for general scenario. To protect the privacy information with a single input, I propose to use dynamic noise injection with a self-attention module and a dynamic noise injection module. This figure shows an overview of our method. PriPro can be directly injected into a deep model between edge and cloud. The self-attention model here is to identify the importance of information from different positions. The importance will be used as weights for noise injection. The noise generation module is to generate dynamic noise according to each input for protection. The self-attention mechanism is first proposed by Wang et al. The key here is to learn weight tensor indicating different importance from one position to another. Therefore, this importance is a relative importance from one position to another. However, in this paper, we propose to accumulate the relative importance along the first dimension of the tensor. In this way, we can convert the relative importance to absolute importance. Therefore, we can use the absolute importance as weight for each position to inject noise. Specifically, we add more noise to less important position, while less noise to important position to protect privacy will keep the information relative to the user task. However, adding weighted noise sometimes is not enough. The dynamic noise here, the mean and variance parameter for noise injection is based on input image rather than model training. We can notice that if we have better parameter for noise generation, the protection will be much effective and take less influence on user task accuracy. The method we propose is to use the transfer model, consists of a simple linear layer. The transfer model will take the mean and variance of the intermediate result as input and output mean and variance of noise. Learnable parameter make the whole module suit the user task and input images better through optimization. Finally, We combined the two modules with a weighted sum between the noise and the intermediate results. It is also shown in our figure you can see here. The advantage of PriPro is clear. First, we apply protection for each input. This is suited for edge cloud synergy. Second, PriPro can be applied to any trained model by injection. There is no need to retrain the parameters or change architectures of the original model for user task. Third and fourth, the protection is applied with awareness of user task and no assumption about the attacker task. Therefore, PriPro can work better in general. Finally, the computation overhead is low. We will show in our experiments later. For the third part, I will show the evaluation results of the proposed PA and PI metric and the PriPro protection method. Before I start to show the results, here is the general setup of our experiments. We use PyTorch for model implementation and Entity Toolbox for MI computation. All our experiments are conducted on V100 GPU server. We use XNight, ResNight, and VGG model to perform privacy protection. They are all famous models in computer vision area. We set up two scenarios for protection and attack. In scenario A, the user task is an image classification on a subset of ML image, and the attacker task is to identify human on VOC 2012 dataset. Scenario B is similar to the Shredder. There, the user task is a gender classification on VGG phase 2. The attacker task is an identity classification on Celebrity A dataset. The accuracy for each model and task is shown here. Before we use PA and PI for evaluation, we need to confirm the efficiency of PA and PI metric. We confirm this by making a comparison between PA and PI and MI metric. This figure here is the same as before to show that MI cannot reflect the protection effect efficiently. Right triangle here is the MI reduction, and bar here is the accuracy of attacker. We are expecting that higher MI reduction leads to lower accuracy of attacker, but this is not the situation. This reminds us MI is not efficient enough as a metric. The table on the right shows results for the same experiment with PA and PI. It is clear that higher PI indicates lower accuracy on attacker task, which means more effective protection. Such results indicate that PI is consistent with the real-world scenario. Therefore, PA and PI can reflect the protection effect more accurately than MI. After this, we can use PA and PI to evaluate PriPro and other methods for fair comparison. In this page, we make a comparison between Shredder and PriPro. The PA and PI for Shredder is on the left, and right for PriPro. We can notice that PriPro can improve PI significantly compared to the Shredder. This indicates PriPro can protect privacy more effectively than Shredder. As for PA, we notice that PriPro can keep a PA at the same level as Shredder. This indicates that PriPro does not have much influence on the user task, which is usable in the real-world scenario. We also conduct some evaluation study to show the effectiveness of either module in PriPro. As shown in the figure on the left, SA stands for the self-detention module and NG stands for noise generation module. We make comparison here by adding either module directly to the architecture of Shredder and show the results. If we only use one module, noise generation can bring more increase in the effect of privacy protection indicated by PI. However, NG plus SA, which is the proposed method called PriPro, is always the best. Here, NG plus binary means we replace the weight with a binary tensor. This is also an evidence showing that the effect when combining SA and NG module. The figure on the right shows the computation overhead caused by PriPro within the model to protect. For each pie graph, purple portion, like this, is the overhead of PriPro. We can notice that comparing two flops of the user model on edge and on cloud, PriPro only needs a small portion. This result shows that PriPro can be used on edge device for privacy protection. Further, we make a visualization for the important weights generated by the self-attention module. In each photo, letter places are more important according to the weight. We notice that letter places are also most related to their semantic label. In this case, we know that self-attention module can provide accurate importance indicator. As for the noise generation module, it needs to converge to different value to provide both stable and diverse parameter for noise generation. Therefore, we show the generated variance from noise transfer model in the right figure. We can notice that through optimization, the output value will converge, and the converged value is different between different inputs and different channels. This is the expected results, and this shows that our noise generation module can work very well. We also conduct analysis on cutting points for edge-cloud synergy on different models. For more results, please refer to our paper. Finally, I will present the conclusion and talk about the future of our work. As a conclusion, PA and PI is a practical metric for privacy protection. I might suffer from the gap between theory and real-world scenario. However, PA and PI is more consistent with real-world scenario, and PA/PI can do evaluation focusing on single-user input. Besides, the privacy protection method PriPro proposed in this paper can provide more effective privacy protection. It is shown that dynamic noise injection can provide effective protection for privacy. And to solve the privacy breach for inference, consider the scope of single-user input is very significant. Further, I also want to share some direction about the future of our work. First, self-attention module is only one method. We also notice that with self-attention itself cannot bring too much improvement to privacy protection. Therefore, better ways for noise injection should be able to bring much improvement. Second, we only focus on protection on computer vision model in the paper. As future work, we will also try to handle other deep learning tasks such as neural language processing. Finally, in edge-cloud synergy, there is a trade-off between privacy and computation cost on edge for different cutting points. For PriPro, we rely on manual selection of cutting points. We will try to make the whole process automatically when applying PriPro in edge cloud system. That's all for my presentation. Thank you for listening.